Swayam Prabha. Digital India. Educated India.
Thanks for the session. Welcome to the session AI for complex systems. My name is Yoshiyuki Yamashita from Tokyo University of Agriculture and Technology, and I will chair this session. So the first presentation is Mr. Yusuke Fujimori. Are you online?
Can you hear me?
Okay. So please start.
Hey. Thank you. My name is Yusuke Fujimori. I would like to talk about multi-objective heat exchanger network design support system using reinforcement learning. The first is the research background. Heat recovery in chemical plant design requires engineers' knowledge and experience, which is a heavy burden. The heat exchanger network is multi-objective, and since this system produces a large number of hand, automation of the system is required. Therefore, in our laboratory, we have constructed a heat exchanger network design support system using multi-agent. In this lower figure, horizontal arrows represent heat exchanger fluid, and the circle and lines represent heat exchangers. This figure representing a heat exchanger network. This heat exchanger network will be called HEM from now on. HEM's evaluation index has trade-off relationships. And multi-objective evaluation is required, but the weights of the evaluation are ambiguous, and it is difficult to set the evaluation acts. Therefore, among the hands designed, we would like to present hands that palette solutions as alternative plans. And users can select the plans they want from among them. For example, this circle point is a space-saving plan with an excellent evaluation of the heat transfer area, although the evaluation of the cost is not good. This circle point is a cost-oriented plan with a poor evaluation of the heat transfer area, but an excellent evaluation of the cost. While the conventional heat exchanger network design support system can obtain various plans, it also many plans that are not useful. I would like to be able to cut off the search for plans that are not useful, like this. Therefore, the purpose of this research is to efficiently obtain useful plans using reinforcement learning. I explained the heat exchanger network search method of this system. First, create an initial HEM from process data and temperature difference constraints. Next, using the initial HEM as a starting point, a search is performed using simplification of the substructure. All HEMs obtained in this research process are candidates for alternative plans. This system uses a technique called strategy switching method to search for HEMs. The strategy switching method is to give different strategies to the agent who design hen called handler. Simplified hen is passed to other handler, and by switching the strategy, various hen can be obtained. For example, handler B receives hen A3 and simplifies the fourth move to become hen A3 B4. However, in order to efficiently obtain useful plans, it is necessary to properly select handler to switch to. So, reinforcement learning was introduced. Reinforcement learning is a learning method that rewards the result of a series of actions of the agent instead of giving the correct answer for each action of the agent. I will explain the state definition of reinforcement learning. Created hens are classified by clustering. The cosine similarity between each hen vector and virtual centroid of each cluster is calculated using this formula. And the cluster with the highest similarity is assigned. Then the center of gravity is recalculated within each cluster, and the operation of assigning it to a cluster with a high degree of similarity is repeated. When the center of gravity hardly moves, clustering is complete. Hen vectorization uses such substructures. In the lower left hen, there are three substructures A, 1B, 1C, and no D. The structural features of hen can be extracted by representing how much and what kind of substructure hen contains as a vector in this way. Then, compute the cosine similarity between this vector and the centroid of each cluster. Next is action definition. The agent chooses the most valuable action given the situation in which it is placed. The correspondence table between the agent's states and action is called the Q table. The action in this research is the operation of switching, passing the created hen to another handler. For example, this circle represents the value of taking action A in the state of 1. Handler performs switching based on this Q table. Before running, all squares have a value of 0, but by giving rewards, run high value actions in each state. Next is reward design. In this system, among the created hen, palette solutions are called alternative plans. And the value of usefulness and diversity uses items to evaluate the alternative plans. First, usefulness. Plot the alternative plans in the rating space. Take out the diagonal component of the evaluation value vector. The average value in the set of alternative plans is called usefulness. If the value of the evaluation index of the alternative plan is large, the usefulness will also take a large value. Diversity is the degree of coverage of the space. When the alternative plans are projected on the space perpendicular to the diagonal of the evaluation space. The more widely distributed the alternative plans, the greater the diversity. As you can see, usefulness and diversity are the values used for the set of alternative plans. The reward for the created hen is calculated from the contribution to the usefulness and diversity of alternative plans at that time. When a new plan is added to the alternative plans, the usefulness and diversity of the alternative plans will change. Contribution is the amount of change in usefulness and diversity of alternative plans at that time. If the addition of the new plan increases the usefulness and diversity, it can be said that it has contributed, and a good reward will be given. Thus, contribution is value used for one plan. I will explain the flow of reinforcement learning in this system. First, hen A creates hen A1. Next, convert this hen A1 into a state by judging the structure of hen. Then refer to the Q table that hen A has. In this lower left figure, A1 is in state 1, so the value of passing hen to hen B is the highest, and the switch destination is hen B. Given hen A1, hen B simplifies this to create hen A1 B2. Then, hen leader, who is hen's boss, calculates the value of hen A1 B2, and accordingly gives hen A a reward for giving hen A1 to hen B. Then, hen A updates the value of giving hen to hen B in the state 1 of own Q table. This flow is repeated many times during the search for hen. A simulation was performed for a small-scale process. No running in the table is the result of exhaustive search before the introduction of reinforcement learning. And the simulation result of introducing reinforcement learning into reinforcement learning. By introducing reinforcement learning, the total number of hens created and the number of switching times have decreased. So the number of searches has been reduced. Also, the value in parentheses is the number of alternative plans that could reproduce the 231 alternative plans finally presented in the exhaustive search after the introduction of reinforcement learning. It turned out that the no-learning alternative plans was well reproduced. However, the calculation time of reinforcement learning is longer than that of no learning. And it is difficult to apply it to the large-scale process. Conclusion and future. In the heat exchanger network design support system, by introducing reinforcement learning, we were able to make appropriate switching and improve search efficiency. However, the calculation time increased due to the load of learning such as the state judgment processing. In the future, we aim to shorten the calculation time by using deep learning to search for hen. Thank you for listening.
Okay, I have similar questions, and as first, in your simulations, how did you determine when simulation finished?
Okay. We cannot simplification. We cannot simplification of hen in such.
Okay. And one more question, and maybe the agents uses the substructions, right? Substructure. Yeah, I want to ask about the substructure. Yes.
Hi.
And, so how did you decide which substructures are used in the simulations?
First, heat exchanger. A number of heat exchanger is smaller than 4. Small 4 and.
Okay, I have a question. Did you determine the substructure in advance, or the substructures are determined automatically? Which one?
Advanced or the automatically.
So you chose substructures examples, or they are outputs from the agents?
Okay. Advanced to determine.
Okay, thank you.
Hi.
Okay. So no other questions? If no, let's move to the next presentation. Thank you.
Thank you.